Hi students, welcome back to 3 Inquisitive Kids. In this video, we will be learning about something called the scientific notation. Lesson 10, Introduction to the Scientific Notation. Again, this is our course outline of the unit. In our last lesson, we learned about exponents with rational numbers, and this lesson ties in very well into our previous lesson. Our learning goals for today is to be able to express large numbers using the scientific notation and be able to convert numbers from standard form into the scientific notation and vice versa. I want to ask you a question. How many stars are up there in the sky? At the International Astronomical Union Conference in Sydney, astronomers pointed out that there are about 700 trillion stars in the entire visible universe, which is more than the sum of all the grains of sand in the deserts and beaches on Earth. If you really want to write out this number, you would need to write 22 zeros after a 7. Approximately this much stars. Let us feel 1 light year together. 1 year is 365 days, and the speed of light is 300,000 kilometers per second. And we know that 1 light year is equal to 365 times 24 times 60 times 60 times 300,000 times 1. So that is how much kilometers 1 light year is. So this would be our thousands, hundred, thousands, millions, billions, and I believe this is trillions. So 9,460,800,000,000 kilometers. That's about 1 light year. What do you think? And how do mathematicians express big numbers like these? If a mathematician was going to do a very big calculation, would they have to write out these numbers over and over again, or is there a more efficient way? Here is a scientific notation. I want you to compute the following. 10 to the first power equals 10. 10 to the second power equals 100. 10 to the third power would be 3 tens multiplied together, which is 1,000. 10 to the fourth power, based off of what we learned in the last lesson, it's 10,000. 10 to the fifth power is 100,000. And 10 to the 10th power would be a 1 with 10 zeros after it. What is the relationship between the exponent and the number of zeros in the calculation result? Well, we can see that when the exponent is 1, there is 1 zero in the result. When the exponent is 2, there are 2 zeros in the result. When the exponent is 3, there are 3 zeros in our answer, and so on. So when we have 10, this is essentially just 10 to the first power, so the exponent is 1. And 10 to the second power, the exponent is 2. 10 to the third power is 3, 4, and 5. And in the product, there is 1 zero for 10. There are 2 zeros for 10 squared. There are 3 zeros for 10 cubed. There are 4 zeros for 10 to the fourth power, and there are 5 zeros for 10 to the fifth power. And the total number of digits in the product, including the 1 that you always write in the beginning, would be 2, 3, 4, 5, and 6 for each of these expressions. You can see that the exponent always equals the number of zeros in the product, and the total number of digits in the product is always the exponent plus 1. Here we have 400,000. That equals 4 times 100,000, and we know that 100,000 is 10 to the fifth power. So here you can see that this is the original position of the decimal point. And we're going to move it 1, 2, 3, 4, 5 times. So this is turned into 4 times 10 to the fifth power. You can see that after we move the decimal point, this becomes a 4.00000, which is just 4. 400,000 is equal to 4 times 10 to the fifth power. For 25,000, it's the same thing as 2.5 times 10,000. This is the original position of the decimal point, and we're going to move it to the left 4 times. So we have 2.5, and since we moved the decimal point left 4 times, it's actually 4 times. I don't know why it says 5 times here. the exponent would be 10 to the fourth power. Here's our third example, 5,034. This is the same thing as 5.034 times 1,000. This is the original position of the decimal point, and we're going to move the decimal point left 3 times. And here it's supposed to be 3 times. So that's how we got 5.034 times 10 to the third power. If you move the decimal point left 3 times, then the exponent is also 3. If you moved it to the left 2 times, the exponent is 2. Write the following numbers as powers of 10. 100, 10,000, and this number. Well, all you have to do is really just count the zeros. So 100 would be 10 squared, 10,000 would be 10 to the fourth power, and this number would be 10 to the 8th power. If you counted, it would be 8 zeros. For the second problem, we have 300, which equals 3 times 100, which equals 3 times 10 to the second power. 32,000 equals 3.2 times 10,000, which equals 3.2 times 10 to the fourth power. And since we already know that this number is equal to 10 to the 8th power, then the exponent will be 8. And so this expression would be read as 3.45 times 10 to the power of 8. Example 1. Determine whether the following expressions are written correctly using the scientific notation. The first expression is 1.5 times 10 cubed, and that is correct. The second expression is 29 times 10 to the fourth power. And this is actually not written correctly. Whenever you are writing the scientific notation, there can't be any tens or hundreds places. The biggest place is always the ones place. So if you were to actually write the second expression correctly in scientific notation, you would write it as 2.9. The digit furthest to the left is always in the ones place. It would be 2.9 times 10 to the fifth power. Expression number 3 is also wrong. This 3 actually has to be in the ones place. So if you wrote it correctly, it would be 3.2 times 10 to the second power. And the fourth one is also incorrect because this 100 is not in the form of 10 to the nth power. It's not in exponential form. Which of the following expressions is written using the scientific notation correctly? And which of the following expressions has 3,080,000 written correctly in the scientific notation? For the first question, our answer would be D. You can see that A is not an option because 25 is in the tens place. If we were to actually write it correctly, it would be 2.5 times 10 to the fourth power. So A is not an option. B is also incorrect because this 3 is not in the ones place. C is incorrect because you can see that there are no exponents, first of all. And if you were to actually write this correctly in scientific notation, it would be 3 times 10 to the third power. And so our answer is D. For the second problem, our answer would be C. The digit furthest to the left is in the ones place, and it's being multiplied to a 10 to the power of blank. Which of the following equations are invalid? When finding the value of a number written in the form of a times 10 to the nth power, which is scientific notation, you move the decimal point to the right of a by n places. You can use 0 as a placeholder. For instance, if we have 3 times 10 to the fifth power, this is where the decimal point starts. This is the original place of the decimal point. And you move the decimal point to the right 5 times because 5 is our exponent. 1, 2, 3, 4, 5. And then we use 0 as our placeholder. We're left with 300,000. And so our answer to this question would be D. Expand your thinking. The average heart rate of a normal person is 70 beats per minute. How much does the heart beat in a year? Express your answer in the scientific notation. Can a normal person reach 100 million heartbeats in a lifetime? Let's say that one lifetime would be 100 years. First, you have to do a lot of multiplication. We know that one person beats 70 times per minute, and there are 60 minutes per hour, and there are 24 hours per day, and there are 365 days per year. When you multiply that, you get 36,792,000. And that written scientific notation would be like this. And in a lifetime, it would be our answer times 100 because there are 100 years. So we would be left with 3,679,200,000 heartbeats. And since this is greater than 100 million, yes, a normal person's heartbeat can reach 100 million times in a lifetime. And so this is our answer. Today we learned about the basics of the scientific notation. We know that it's a mathematical way to express larger numbers. And the relationship between the exponent and the number of digits in the number can be expressed in the scientific notation. Of course, this is only the introduction to learning the scientific notation. When we get to 8th grade and 9th grade, we will build off of what we learned and dive deeper into the realm of exponents and the scientific notation.